I think everyone knows what this means. Garbage in, garbage out. You could say the quality of results of a simulation model are the lower of the quality of the model and the quality of the data. So no simulation model can be better than its input data. If the model is wrong, and that's how to do the modeling, which is a whole other topic and another webinar, the results can be a great deal worse. Now, when looking at data, here are some of the questions to ask. The model needs tool changes per day, and the user has tool changes per month. Well, that looks pretty obvious, but I've seen people get that mixed up. Well, we need a cycle time. Which one? Well, maybe the machines in the two plants are alike. They are the same model. Well, maybe one machine is better maintained or has a more skillful operator. Or for some other reason, the cycle times are a little bit different or a lot different. And is tomorrow's schedule going to be like today's or yesterday's? The number of sales may not equal the number of demands. Maybe demands were made that we were out of stock on. Model needs number of parts riveted, and the user has number of pallets of parts that came in to be riveted. Oh, that's easy. You just divide by the number of parts on a pallet. Well, maybe it's not so easy. Maybe the number of parts on a pallet can vary with the size of the parts, or how vigorously the worker putting the parts on the pallets works, or how heavy a pallet he's willing to roll around. So all sorts of interesting considerations come up here. Almost the moment the person gathering the data, and that may or may not be the person building the model, as soon as the person gathering the data begins to look below the surface. So what do you do about it? Well, you could collect the exact needed data at a price that's a significant expense, typically in both time and actual dollars. You could collect it yourself. You can have contractors come in and do the collecting for you. Make sure you tell them exactly what you want. Or you could extrapolate, like the example of saying, we don't know tomorrow's schedule yet, so we'll use yesterday's. If you do that, for goodness sakes, document the assumption. I put that in italics for a good reason. Any assumptions like this that are made, such as we used yesterday's schedule to run the model predictions for tomorrow, or we assume the number of parts on the pallet is always the same. If you make an assumption, write it down. And one of the most powerful techniques, it takes a little more time, but this can produce marvelous results. Now, suppose the old machine has 5% downtime. The salesperson takes you out to a lovely lunch and claims 2% downtime for the new model of the machine. So which percent downtime do you put in the model? Well, the answer is you put in both, first one, then the other, which in good simulation software takes very little time. And then you compare the results. You may find that 5% versus 2% makes almost no difference. That machine was not the bottleneck. Or you may decide that it makes a great deal of difference. The model says productivity will be much higher as soon as downtime on that bottleneck machine goes down. Well, now you're making progress. You go back and tell the salesperson what your modeling efforts told you, and you tell the salesperson, in view of the importance of this lower downtime, we'd like to put a penalty clause in the contract on whose basis we might buy this new machine. And salesperson A might say, Why, certainly, we're willing to do that. We're confident in the machine. We've torture tested it under bad conditions of temperature or contamination, and we're competent in its low downtime performance. Salesperson B might say, oh, well, wait a minute, I have to go back to the office. I have to talk to our lawyer. Well, now you don't have the new downtime yet, but either way, you've uncovered valuable information. What you've just done is called sensitivity analysis. You're examining how sensitive is the model, and therefore the real system, if the model is valid, to changes in input data that are admittedly uncertain. And those results should be vigorously documented. Well, if you have no data at all, you can do an even bigger version of the sensitivity analysis I've just described. And you can ask an expert. I'm reminded when I say ask an expert, years ago when my vision was good enough that I could shoot pool as a hobby on weekends, the pool hall owner got tired of arguments. So he put a sign up on the wall that said, expert advice available from anyone in the room. So pick your expert carefully. And you ask the expert for that. And then you can use a uniform distribution or a triangular or even a beta distribution. Lately, in statistical conferences and expertise, beta distributions are getting more favorably looked on compared to triangular. The point of all three of these distributions is they have a firm lower and upper bound. They cannot go negative, and their upper tails cannot go out to infinity. There's a histogram of some random data generated by a software package, and of some triangular data, and of some beta data. So another way to choose is go into the package, put in some parameters, look at the histogram, and ask your expert, such as the person who runs the machine or repairs the machine, ask the expert which of these bar graphs, histograms, looks the most like what you'd expect to see over the long haul. And then you have a good basis for using that distribution. Now, even after you get input data, there's some important statistical questions to ask. And for one of the subtle ones, is it autocorrelated? And here's an example of autocorrelation. One of the projects I worked on a couple years ago was one of those drive-through oil change shops. And some of the drivers had their transmission oil drained and changed. And some of the drivers also had their transmission fluid drained and changed. Now, it turned out on examination that if a car or truck needed more time to drain the oil, it probably needed more time to drain the transmission fluid. Bigger car, bigger truck, bigger engine. That's an example of correlation. The input data is correlated in a sense with itself or with other closely related input data. And that can have a big effect when there is positive autocorrelation. Bigger tends to go with bigger. That's usually worse. The Q-links tend to get longer, other things being equal. So don't forget to look for autocorrelation. Oh my, if you just took your input data out of a spreadsheet and sorted it and threw away the original, maybe it was handwritten, oh, I hope you didn't lose the time order in which the data were originally collected. Don't let that happen to you. Always keep the raw original time order of collection data so that you can go back and look at these issues anytime you want to. And is the data time dependent? Which day of the week, which week of the month, which shift? For example, the night workers may be less experienced and less skilled than the day shift workers because the day shift is preferred and they have seniority. So that's another thing to look at. Does it range include maybe the data you collected, an extreme case like an unusually long repair went up to 8 minutes. Maybe at worst, it could be 20 minutes. So maybe you need a long, skinny tail. And related to the autocorrelation, do observations tend to get gradually longer or shorter over time? Are the operation times getting shorter because the worker's getting used to doing the work? Are they getting longer because the worker is getting tired as the shift proceeds? That would be a violation of independent, identically distributed data. And independent, identically distributed is what that commonly used nickname stands for. And then once you feel you understand all these things about the data, how do you put it into the simulation model? Well, you can put it in directly by giving the model all the data points in a file and letting the model sample among them directly. That's what number 1 refers to. Or you could fit a statistical distribution like Weibull, log normal, gamma, beta, and so forth by using one of 3 commonly used packages that do exactly that work. And the package can be told to use any one or all of these methods whose fancy names I put on the slide. And if you find a good fit, number 2 is actually preferred. You may not find a good fit. If you don't find a good fit, you may have to use number 1. But if you don't find a good fit, first take a quick look at your histogram of the data. You may find the histogram is bimodal or even multimodal. That would mean that the histogram has 2 humps. Then almost certainly you don't really have one data set. You have 2 data sets. You just didn't know it yet. For example, you thought you had one data set. How long does it take to repair the drill press if it goes down? Well, really, you have 2 data sets. How long does it take to repair the drill press if it jams? How long does it take to repair the drill press if the motor fails? That's 2 different data sets. Now you work with each one of them individually, and you find perhaps that 90% of your failures are due to jams and 10% are due to motor failures, and you use your 2 repair time data sets accordingly. And how do you run the model? The model, if you're working with a model of a manufacturing or warehousing process, it is probably steady state. That means the model picks up Tuesday morning where the work left off Monday morning. If you're modeling a bank service to the customers, that's much more likely to be terminated. The bank closes and empties at 6 o'clock at night, and it opens empty at 9 o'clock the next morning. So assuming your model is terminating, the correct warm-up time is 0. If your model is steady state, or actually I should say your system is steady state, you want to run the model as steady state. When you begin running the model on the computer, it's empty, but that's an abnormal situation. You don't want it to contaminate your model results. So you tell the computer, run the model for a while, and throw away the statistics Now the model is reasonably full, just like the real system. You run it and gather your statistics on performance measures. Well, I said you run the model for a while. And how long is a while? Maybe a day, in simulated time, maybe a week. Charting and running various statistical tests can tell you how long the warm-up period should be. And maybe you can shorten it if it's way too long by starting the model with some work items artificially introduced into it. And also to build confidence intervals for your performance metrics, how many replications are needed? Maybe 5, maybe 10, maybe 20. I do know that you need more than one, because each replication is a random experiment of running the simulation models with random numbers generated by the software. And keep in mind, in the statistical formulas you may remember from way back when, there's a square root of sample size in the denominator. So if you want the confidence intervals to be half as wide, you're going to need 4 times as many replications. And you also want to ask yourselves, when you're going to use the model results, what are the answers to the questions on this slide? Do you want a better or worse, like qualitative, or do you want hard numbers, such as, can a certain system produce 45 jobs per hour? The quantitative need longer runs and more accurate data. And what level of confidence are you going to use for your confidence intervals, for your performance metrics? It might be 90%, 95%, 99%, something else. Those 3 levels are the most common. And if you have a lot of alternatives to look at, say 10, do you want to begin by selecting the best 3, 1, 2, 3, or in any order, for further, more detailed comparison? Or if you have 10 systems, do you want to select a subset of size 3 guaranteed to contain the best one at, let us say, 95% confidence for further study? And here's some examples coming up, all based on manufacturing. One was all of these are projects I've worked on. And here's an example. You can see what we had to do at the sunglasses factory. You don't usually think of manufacturing sunglasses, but that's exactly what was being done. And all of these input data had to be collected and documented. For example, this 5th item, you had a product mix. And this analyst working with the clients is very typical. Distribution fitters were used, and simulation software nowadays supports import from Excel very conveniently. Usually we recommend that. Then you have your data all safe and sound inside an Excel workbook that can be documented, made easy to read, made very large, pivot tables, and so forth. Here's a second example. This was a typical flow shop. So there were many different flows. And the machines were in cells, which was not true in the previous example. And we had changeover times. There may be changeovers when the type of part is changed, or after a machine has run 10 operations, or for whatever reason. There's a variety of reasons that changeovers are necessary. And if changeovers are necessary, then when they're necessary and how long they last has to be carefully documented. And an interesting caution here, the changeover from part type A to part type B was not always the same as the changeover from part type B to part type A, which was useful information to give the model. It affected the user's scheduling policy. And rarely for manufacturing, usually manufacturing simulations are steady state. This one was terminating. Okay, we power up the shop, we've got a rush job. How long will it need to fill a rush order? And if the workers need to travel around, how fast do they travel? How far do they travel? Do they travel slower if they're pushing a cart or carrying a heavy box? That has to be checked. In a healthcare simulation, the same issue comes up. A worker on a gurney, worker pushing an empty gurney might walk down a long hospital corridor quite quickly. If the worker is pushing a gurney with a blood transfusion bottle and an oxygen mask and an unconscious patient on it, the worker may have to rush faster or, out of caution, may have to proceed much more slowly. That would be interesting and important data to have. And here's a third example, painting aircrafts. And this illustrates the interesting point. Simulation often, and it did here, it combines beautifully and very powerfully with value stream mapping and time studies. And happily, the client already had a lot of the data from those efforts. That's one good reason to combine them. And we needed and gathered additional data needed, downtime and repair time data. In fact, in detail, that's a whole nother webinar. Not only how long does the downtime last, but how long does the machine operate correctly before it goes down again? And that uptime might be based on clock time, busy time, or number of cycles the machine performs before it needs repair again. So that consideration is highly important. And as a sort of closing example from healthcare, I can't resist. I've just returned from the annual Institute of Industrial Engineers conference. I mentioned the example of the gurney. Another example that came up at the conference was a phenomenon called bed hiding. Well, there's an open bed on the hospital floor, and the emergency room is very crowded, and a patient in the emergency room has been stabilized and can now be moved to the hospital. But the emergency department people don't know that that bed is vacant. The nurses on the floor never said so. Well, that's understandable. The nurses on the floor are terribly overworked and understaffed already. And a similar phenomenon that was reported in a case study at the conference was called bed blocking. A patient is almost completely recovered and can be sent safely home. Now, this patient represents relatively low workload for the overworked nurses on that floor. If they push to discharge the patient, the bed will almost immediately be occupied by another patient who's almost certain to be sicker and increase the workload on nurses who are already overworked. So those all bring up interesting points on the subtleties that can arise on exactly this same topic in the context of simulation for delivery of health care in hospitals, emergency departments, therapy centers, nursing homes, and clinics, which is another topic of high interest these days.